Hi guys, welcome to my channel. So this tutorial is about resonance, an organic chemistry topic that will haunt you for the rest of your Ochem journey, okay? So let's jump right into it. So I listed 4 types of situation where resonance can happen. These are the 4 types of Ochem 1 situation where your professor can ask you to draw the resonance structure on your exam, on your homework, things like that. It looks overwhelming at first. It's okay. We're just gonna go over each one of these one by one and try to make it super clear for you guys, okay? All right, so first off, I have a structure here. Let's label everything. So here I have a positively charged carbon. Here, my positively charged carbon, that is next to a double bond, okay? My double bond, my positively charged carbon next to a double bond, okay? So before we try to draw the resonance structure of this structure, I would like you to know that whenever we see a positive carbon, we know that this carbon doesn't have its ideal 4 bonds, right? It has 3 bonds. So I already have 1, 2 bonds here. So the third one must be the hydrogen here, right? That will give me the formal charge of this carbon. 4 minus 3 equals plus 1. So that's where my positive charge of this carbon comes from, right? We ignore the 1. We say it's a positively charged carbon. Okay, perfect. So the same thing for this carbon. Sorry. So this carbon is neutral. We don't see any charges, right? We don't see positive sign, negative sign. It is neutral, which means it is a neutral carbon. So it must have 4 bonds, right? We already have 1, 2 here. So the other 2 bonds must be hydrogen. That will give me a formal charge of 0. So it's neutral. It doesn't have charge at all. Okay, perfect. So now let's start to draw the resonance structure. Okay, so what happens when resonance happens is the double bond will move itself like a door hinge. It will be swinged to this side. Okay, so let me draw the structure after the movement of this double bond. Okay, so it was originally here, but it's not here anymore. It's here, right? Okay, so this movement would change the charges of a couple of carbons. Okay, let's take a look at this carbon. So this carbon, the same carbon here, right? I never lost this hydrogen here. This hydrogen is still here, okay? So if you pay attention to the number of bonds, you can see I have 1, 2, 3, 4 bonds of this carbon, which gives me a formal charge of 0. So this carbon is neutral. So do I copy and paste this positive sign over to this carbon? No, because it's neutral, right? Okay, so this is the case for this carbon. But if we take a look at this carbon, I still have the 2 carbons that I never lost, right? These 2 carbons that I never lost. But the thing is, I lost a bond, right? I originally had this bond here, which gives this carbon 4 bonds. But now I only have 1, 2, 3 bonds of this carbon, which gives me the formal charge of positive 1. So this carbon would have a positive charge here, okay? After the movement of these electrons. Okay, let me clean it up. So after I clean up the hydrogens, you can see that my final structure of this problem will be this, okay? This will be the answer I put on my exam, okay? Perfect. Once again, we have a positively charged carbon here next to a double bond, okay? So the double bond move itself to here like a door hinge. Thus, I created a new double bond here, and then that changes the charge of this carbon and this carbon, okay? This carbon goes from positive charge to neutral, and then this carbon goes from neutral to positive. Okay, perfect. Now let's move on to the second situation. So once again, let's label everything. So in this case, I have a positively charged carbon here next to an atom with lone pair. Okay, you say, okay, I'm sorry, let me use this color, okay? Next to an atom with lone pair. You say, okay, I see an atom here. But you have to know that oxygen has 2 sets of lone pair, right? Why? Because my oxygen here is neutral. It doesn't have any charge. its formal charge is 0, which means it satisfies octet rule. Octet rule means you have 8 valence electrons, right? Okay, this bond here represents 2 electrons, right? This bond here, 2 electrons. So oxygen would need 4 more electrons to satisfy the octet rule, which is for 8 valence electrons. So I need 4 more, right? So these 4 more electrons would make up 2 sets of lone pairs. Okay, perfect. So now I have my my atom with lone pairs next to my positively charged carbon. Okay, let's see who's gonna initiate the process of resonance. Okay, in the first example, it was the movement of the pi bond. In this case, it will be the movement of the lone pair, the 2 electrons, aka lone pair, right? Okay, it doesn't matter if it's this set of lone pair or that set of lone pair that moves. What you need to know is resonance is essentially the movement or rearrangement or redistribution of electrons. And whether it's the double bond or the lone pair, they represent the relative abundance of electrons, right? Double bond compared to a single bond, double bond has more electron density. And since lone pair doesn't participate in any bonding activities, so these electrons, that they're more they're more prone to any sort of movement, right? Okay, so now let's move the lone pairs, okay? So it doesn't matter which pair of, which set of lone pair I choose, I'll just choose this set, and then I'll move this lone pair here to create a double bond, okay? So let me create this double bond first. Okay, so I still have this set of lone pair here, right? But this set of lone pair is gone now because now I have this double bond, right? Okay, now let's see what's the consequence of this movement, okay? So let's pay attention to the oxygen first. So before the oxygen is perfectly neutral, right? It has 2 bonds, 2 sets of lone pairs. So the formal charge is 6 minus 6 equals 0. Thus, we don't have a positive sign or negative sign by oxygen. Whereas this oxygen here, if we count the number of the bonds and the electrons, we would know the formal charge now is 6 minus 5, right? 1, 2, 3 bonds, and then 4th electron, 5th electron. 6 minus 5 equals positive 1. That would give my oxygen a positive charge, right? Okay, so let me clear everything. Okay. To just give this oxygen a positive charge. Okay, now let's also take a look at this carbon here. So originally this carbon has a positive charge, which means it has how many bonds? 3, right? It has 3 bonds. So the formal charge of this carbon will be 4 minus 3 equals 1, positive 1. So I have this positive charge here for this carbon. Whereas I never lost this hydrogen. And then now this carbon has how many bonds? If you were to count it, 1, 2, 3, 4, right? Because of this extra double bond that we just created due to the movement of the lone pair, now we have 4 bonds of this carbon. So my formal charge will be 4 minus 4 equals 0. So my carbon doesn't have any charge here. I don't need to copy paste this positive charge here. It is just a neutral carbon now, right? It lost the positive charge that it had before. Okay, perfect. Now let me clear clear the mass. Okay, and then just give you a nice picture of my final structure of this problem. Okay, this is the structure I would draw on my exam. Okay, once again, I have a positively charged carbon next to an atom with lone pairs. Thus, I remove the lone pairs to here, creating a new double bond. Thus, I changed the charge of this oxygen from neutral to positive, and then the charge of this carbon from positive to neutral. Okay, perfect. Okay, now let's do a more complicated problem that combines both situations, situation 1 and situation 2, okay? So let's copy and paste situation 1 and 2 so that we can look at our situation and then compare the wording to our structure, okay? Okay, perfect. So looking at this structure, right off bat, I see 3 things. I have a positive charged carbon, I have a double bond, I have an oxygen, right? Okay, then I was thinking to myself, okay, this oxygen is an atom with lone pair. True. That is so true. Okay, but this oxygen with lone pair, is it next to this positive carbon? No, they're pretty far away, right? It is not next to this positive carbon, but it's okay. Because why? Because this positive carbon is right next to a double bond, right? They're next to each other. Perfect. So let's forget about number 2. Let's do the movement of what we did for example 1, okay? Okay, perfect. So for example 1, what we did, remember, we moved this double bond to here. We like swing it like a door hinge, right? Okay, so let me draw the structure for you after we move that double bond, okay? So my double bond was here. It's not here anymore, okay? Because I moved it. It's not here anymore. Where is it now? It's here now, right? That's where my arrow goes. Okay, so after I move this double bond, you have to pay attention to the charge again, okay? So let's check this carbon first. So this carbon was originally neutral, right? Because at the 1, 2, 3, and the fourth one must be the hydrogen here. It had 4 bonds, so it's perfectly neutral, no charge, no positive sign. But now I still have this hydrogen here, but how many bonds do I have? 1, 2, 3, right? I had a bond here, but I moved it to here, so I lost a bond. So my carbon now has a formal charge of +1, which will give my carbon a positive charge, okay? Okay, so I label a positive charge here for my carbon. But what about this carbon? So this carbon, once again, it has a positive charge here, which means it has how many bonds? 3, right? It has to have 3 bonds to have a formal charge of +1 to give it this positive charge, okay? So now I still have these 2 hydrogens here, right? These 2 hydrogens was never lost. But I also gained an extra bond. So now for this carbon, I have 1, 2, 3, 4 bonds. This number 2 bond is the extra bond that I gained, right? Due to the movement of the double bond here, right? Okay, perfect. Now this carbon, what's my formal charge? 4 minus 4 equals 0. So it is a perfectly neutral carbon. So I don't need to assign any charge to this carbon, okay? So let me delete all the messy stuff and then just give you a clean structure of my resonance structure, okay? This is the first movement that we had, okay? This is this, okay? When we had a positive charged carbon here next to a pi bond, okay? A double bond, so that we move that double bond here to this position, which changed the charge of this carbon and this carbon, right? This carbon goes from neutral to positive, whereas this carbon here goes from positive to neutral, okay? Perfect, okay. Now, let's look at this structure that we drew, okay? Let's look at this structure. Okay, now this structure, I still have this atom with 2 lone pairs, 2 sets of lone pairs. But now, do I have a positive carbon that is next to my atom with lone pairs? Yes, I do now, right? I do now. Now this positive carbon is right next to my oxygen, which has 2 sets of lone pairs. Okay, so we're gonna do something to this structure, because remember the lone pair is the anti-electrons that want to move, right? Okay, how does it move? It will move to here, right? It would create a new bond here. Okay, so now let's create this double bond. I still have this side of lone pair here, right? We never touched this side of lone pair. We just moved the lone pairs below. And it doesn't matter like which side of lone pair you move, okay? Okay, perfect. Now I moved the lone pairs. I created double bond. Does something happen? Oh yeah, oh yeah. Okay, now let's take a look at this oxygen first, okay? So before my oxygen is neutral, right? My oxygen had two bonds and then 4 electrons. So 6 minus 6 equals 0, right? It is neutral. But now my oxygen has how many bonds? 3 bonds, right? It has 3 bonds, plus I have 2 electrons. So 6 minus 5 gives me positive 1. So my oxygen here is actually a positive oxygen now, okay? So besides oxygen, what other atom changes its charge due to the movement of the lone pair? Okay, let's take a look at this carbon. Okay, so before my positive carbon, once again, I have like 3 bonds, right? So I have a positive charge for this carbon. I still have this carbon. The difference is now I have 1, 2, 3, 4 bonds around this carbon instead of 3 bonds. So this carbon will be neutral now. So I would not have this positive charge anymore. Okay. Okay, perfect. So my carbon will be neutral here. Okay. I don't mean to delete the positive charge for the oxygen. I just want to draw it in black so that it's more consistent. Okay, perfect. So now this is the second resonance structure of my problem, right? So whenever you see a problem like that, you have to draw both structures to complete the solution, okay? Okay, perfect. So now before we move on to the next video discussing the third and fourth situation where resonance happen, I like to draw the resonance hybrid pictures of the 3 examples we did above, okay? This may be asked on your first Ochem exam or quiz, like first draw the resonance structure, and second, please draw the hybrid pictures of your resonance structure, okay? So let's take a look at the first one that we did, okay? So let me clear everything to make it clean. Okay. Sorry about the mess. Okay, perfect. So in this structure, we see that first, I will just use a different color, okay? So first, the problem starts with the positive charge here, right? And then it ended the positive charge here, right? And then we also check out the double bond. We first had our double bond here, and then the double bond moved here, okay? So if I were to draw my hybrid structure, it will be something like that. So first I had my double bond here, and then I had my double bond here, and first I had my partial positive here, and then I had my partial positive here. Not partial positive, I mean positive. So I would assign partial positive charges to these 2 carbons who had positive charges before. So because, to explain this, resonance is not like a one-way reaction. It's an ongoing 2-way activity where the electrons move around themselves, and they ended up distributing the electrons due to the electron movements, right? So that's why we use this 2-way arrow instead of a one-way arrow to draw resonance structures, right? Because they're just transitional structures. Both of these structures, they're just transitional structures rather than the product of any chemical reactions that you would draw like a one-way arrow, right? Okay, so that's why these 2 spots, this spot and this spot, they're never, this spot and this spot, they're never absolutely positive. They're always in this transition of being kind of partial positive, right? Okay, so that explains why we assign a partial positive signs to my carbons who were once fully positive on these structures, okay? Okay, so now number 2, once again, let's check it out. Okay, let's see. So, okay, so my positive charge started here, and then eventually it ended here, right? It started here, this carbon. It was positive. It ended here. And then this position is the only spot where I had my double bond formed, right? Okay, so I would draw something like that, and then I assign positive charge to this carbon and this oxygen, and then this dashed line representing the formation of my double bond, right? Once I have this structure formed, immediately it would go back and forth back to this structure. It's a two-way activity. It happens. It keeps going on and on. Okay, perfect. Okay, so the third one. How do we draw the hybrid structure for this one? This is more challenging because we have a bigger distribution of our positive charges here, okay? So let's see where it started, okay? So we started here, right? This carbon, we started here. It has a positive charge, okay? We started here. And then before this oxygen gained its positive charge, this thing here, this carbon here also had a positive charge once upon a time, right? And then eventually this oxygen here had its positive charge, right? And then also let's check out my double bond. Okay, my double bond was first it was here, and then I moved the double bond to here, and then eventually I moved that double bond to there, right? I have 3 spots, 3 double bond spots, and then 3 positive atom spots, okay? So now let me draw the structure. I have oxygen here, okay? So I had a double bond here, I had it here, and I had it here, right? And then also this carbon was positive once upon a time, and then also this carbon, this oxygen. So I'm gonna assign partial positive charge for these atoms to represent this ongoing process, okay? Perfect. Okay, so yeah, I hope this is clear and helpful. We are gonna discuss the third and the fourth situation in my next video. If you like this, if you like my video, you think it's helpful, please subscribe to my channel. You can comment on my video, and please ask any questions or confusions you may have. And good luck with your studies. See you soon.